Hi girls, how are you? Welcome back. I just wanted to talk to you today about our topic that we're going to be starting with this term, which is dynamic equilibrium. All right, so I just want to give you a quick introduction to that. I mentioned in the email a clip that you should look at to understand a little bit about reversible reactions. So hopefully you've looked at that, and hopefully that's kind of where we're going to start with. Okay, so you're used to chemical reactions where we start with two reactants. It doesn't have to be two, but let's just take two as an example, A and B, and they give us C and D. Okay, so an example of this would be something like when we light a Bunsen burner. Okay, so we take methane and we take oxygen and we put them together and we get carbon dioxide and we get water. And there's no way in hell we're changing that carbon dioxide and water back to methane and oxygen. It's not possible to do for lots of different reasons, some of which are just common sense. But some chemical reactions are a bit like that, where you can turn things back. Okay, and I want to give you a couple of examples of that. So, for example, if we were to take two reactants, A and B, and produce products C and D, there might reach a point where there was enough concentration of those products, C and D, that they would start to react together again to form A and B. Okay, so we'd end up with this kind of cycle where A and B produce C and D. When there's enough C and D to be produced, they produce A and B again, which go on to react to form C and D. And we end up with a sort of a balance, okay, between the two, between A and B and C and D. Now, I can show you this best really with a graph. So I'm going to try and do that now. Okay, I want you to have a look at this graph here. And this is our reactant A. Now, when you did rates of reaction, you would have drawn graphs of concentration of reactant and product, and your concentration would have generally looked like this. Okay, the concentration of the reactant starts high and goes down to zero. That's not a surprise. It all gets used up, right? The concentration of the product starts at zero and finishes at a certain amount depending on how much and what concentration of A you start with. So that's what a graph of a kind of a regular chemical reaction would look like. However, if we take something that's in dynamic equilibrium and we start with our reactant, okay, here, it actually never reaches a point where it gets to zero, because as the product is being produced, it starts to react to produce the reactant again. Okay, so C and D are going to react to produce A and B. So rather than A going down to zero, it actually tails off and reaches a certain point. And now it stabilizes at this point. It never moves from this concentration, because every time one of the A's and B's gets used up to produce a C and D gets used up to produce an A and B. So there's a balance between the two. And this point here, as you can see, where the concentrations of both of these do not change, this is said to be where the system is in dynamic equilibrium. The reaction is still going on. You can see that. It's still continuing, but the rates, the concentrations of them are not changing. All right, so A is now consistent and C is consistent. And we could take a sample of this reaction vessel, measure the concentrations of both of these, and they wouldn't change between this point and this point or beyond. Okay? Now, you can think of this a bit like this. I don't know if this works for you, but we'll give it a go. Another one of my fantastic drawings here, as you can see. This is a shop, okay? And it's a two-floor shop, whatever that's called. I don't even know what that's called. You know what I mean by that. It's got an escalators, right? So this is an escalator up, and this is an escalator down. And I want you to imagine that there's a sale on, right? You know, back in the days when we actually went to the shops, well, this is what's happening here, okay? We're no social distancing here, as you can see. It's absolutely packed, right? So this is just after Christmas. There's a sale on, and there's some fella here at the door stopping people get in, okay? So there's somebody who wants to get in, and he's saying, no, you're not getting in, because it's packed, right? So this is what we call a closed system, right? The shop door is closed. It's absolutely jam-packed. So the only option that people have in here is to go up to the first floor or down to the ground floor. All right? So they go up this side and down this side. And maybe this is men's wear and this is ladies' wear, whatever, right? It doesn't really matter. But the point is that they can only move up or down. For every two people that go up, two people have to go down. And this is a little bit like the reactants and the products. Okay? Because what happens is if two people go up, two people go down. The concentration must remain the same of both here. Okay? It's in dynamic equilibrium. So it's ongoing. There are people on the escalators all the time going up and down, but overall, the amount of people on the first floor and the ground floor doesn't change. And equilibrium is a little bit like that. The reaction is ongoing, but it doesn't change. Okay, now, what can we do with that? Well, what we have to do is we have to know what the concentration of these are. We're going back to our original graph here, right? So I want to show you an example of that. What we can do is we can take a value called the constant, the Kc for this reaction. And the Kc for this reaction is taken by getting the concentration, that's what these square brackets mean, the concentration of the products, that's C and D, and we raise them to the molar ratio. Okay, the molar ratio in this case isn't important because we haven't looked at a specific example yet, so I'm just giving you this so that you can recognize it when we use it later. So we take the concentration of the products and we divide it by the concentration of the reactants raised to the power of their molar ratio. All right, now don't worry about the maths of that. We'll deal with the maths of that later. What's important is the concept. What this is really is the amount of product divided by the amount of reactant. And that gives us a number. Now, if that number is bigger than 1, that means the number on top of this is bigger than the number on the bottom of that. That makes sense, doesn't it? So, for example, in this graph, as you can see, the concentration of the product, C, is higher than the concentration of the reactant, A, in our dynamic equilibrium mixture here. Okay? So, in this case, Kc for this reaction will be greater than 1, right? I want to show you what that looks like. This is what we have here. Okay, so this is our concentration for Kc is greater than 1. However, have a look at this example. In this example, A has decreased. Okay, so the reactant has decreased. The product has increased from 0, as we'd expect. But here, the product never actually reaches the concentration of the reactant. So in this case, in our dynamic equilibrium, which starts from around here, the concentration of the reactant is actually greater than the product. So when we put the products over the reactants is actually smaller than the product. And what we end up with then is Kc is less than 1. So in this case, our Kc value for this reaction will be less than 1. All right, there's one other possible option here, which is where it's very unlikely, but if the reactant decreases and the product increases to the exact same value, okay, you can see those two are on the same point, well then Kc is exactly equal to 1, and that means the concentration of both the product and the reactant is the same in our reaction mixture. So Kc in this case will be 1 because what's above the line and below the line is the same number. Is that okay? So there's 3 different options here for Kc depending on what graph you end up with. If the reactant is greater, higher concentration in the product, then Kc is less than 1. If the product has a higher concentration in the reactant, then Kc is greater than 1. And finally, if they're identical, Kc is equal to 1. Now, I've got some slides in the folder there that go into that in a little bit more detail. And we'll be doing another couple of videos over the next couple of days to help you with some calculations with this. Okay, but today really is just about you getting your head around the concepts here today. And I hope that helped a little bit with that. All right, thank you. Bye-bye.